You got about 1 minute to say what you're going to say. People aren't saying very much. Say more. All right, let's put this down, walk our way through the question that I recognize is difficult, but also I asked you for a reason, which is that it contains all of the pieces that I want you to know about the geometric series approach to finding the power series. So the question asks to find the power series for this one. And the hint you were given was that the derivative of this part, d by dx, the arctangent 2x, is 2 over 1 plus 4x squared. Now, why would that matter? It matters because you actually know how to deal with things that are in that form, because you can take the series for 1 over 1 minus x and just plug something into it. This is 2 over 1 minus 4x squared. The typical move, right? You get something that looks kind of like a geometric series, use the geometric series formula on it. So what I'm thinking the strategy is, when I look at this, is if I could find a power series for that part, I could then multiply it by x in the end, and I would have a power series for the whole thing. Okay? And I know that the derivative of this is in that form. So the strategy is going to be find a power series for this, integrate it to get a power series for the arctangent, then multiply by x. Which is not hard. It just it requires recognizing what the roadmap is to all this. Okay, so this is probably one step too much for a question I would ask you on an exam, but it's here because it has every piece I want you to know. So I'm going to write down what the process looks like. I actually think this is much easier to do in sig notation than otherwise. So if d by dx of the arctangent 2x is equal to 1 over 1 minus 4x squared negative, then that's equal to this series. Right? It's the 1 over 1 minus the box. What do you plug in the box? Well, we plugged in minus 4x squared this time. 1 over 1 minus anything is equal to 1 plus the anything squared plus the anything to the third and so on. Right? It's a typical move of these geometric series type setup. Now, before I do calculus on this, I actually have to get the x's by themselves, or I can't use the power rule. Right now, this x squared is trapped inside this n power. So I'm going to rearrange this as minus 1 to the n, 2 to the 2n, and then x. Oh, there's supposed to be a 2 here. Sorry, I forgot the 2. Okay, is that all right? All I've done is I've taken this. I mean, the 2 is just outside, so there's still this 2 here. Now, the reason that I have to do this is because I'm going to do calculus on this part, but I can't when it's inside because the power rule doesn't apply to it. It has to be x to the something in order to use the power rule when I take the integral. Can I get this extra 2 back inside the series? Because I can multiply it back in, and there'll be another 2 in this pile of 2 at 2n2s. So this is this series in a completely series form. It looks like minus 1 to the n, 2 to the 2n plus 1, x to the 2n. That's the series for the derivative of the arctangent of 2x. So if I want the series for the arctangent of 2x, I have to integrate that. And integration, when you're using sigma notation, is really easy. The arctangent of 2x then is equal to the sum from n equals 0 to infinity. Well, the power rule says add 1 to the power of x and then divide by the new power. And 2 to the 2n plus 1 over 2n plus 1 x to the 2n plus 1 plus c. When you integrate, you have to put a plus c in. Are we done? We got one trivial step left. I use the word trivial there because I was teaching an upper division math class earlier. I apologize. We have one simple step left, right? Which is, I wasn't asked for a power series of arctangent of 2x. I was asked for a power series of x times the arctangent of 2x. But I can multiply powers of x into a power series very easily. That's the arctangent of 2x. So this is x times the sum n equals 0 to infinity minus 1 n 2 to the 2n plus 1 2n plus 1 x to the 2n plus c, and I just distribute the x inside. The x goes in here. So also it's the c. Yep.
You can do plus 2.
Yeah. And when you integrate, you get yeah, the x goes into this 2n plus 1 to infinity 2n plus 2. Now, first question I've got is, does this c, so an obvious question is it really plus cx or can it just be plus c? And the answer is it has to be cx, because when you did this integral, you told me that the arctangent of 2x had a plus c attached to it that we can't figure out unless we have an initial condition for the problem. So this is just some number. But if I take that number and I multiply it by x, I don't get c, I get whatever that number is times x. And if you want to be convinced that this is the way this works, if you put x equals 0 into this function, you get out 0. There shouldn't be a number left over out here. It has to be 0. Okay? So again, this problem has a lot of steps, but no one of the steps is difficult, I don't think. If you see how to get from the top to the bottom, and each one of these steps is something you have to be able to do. You've got to be able to put an x inside of a power series or some power of x into a power series. You have to be able to integrate a power series, preferably from the sigma notation, because that's the easiest way to do it. You don't really want to integrate a power series expanded if you can avoid it. Okay. You have to know how to find a power series for something that looks like a geometric series. All of those steps individually are things that I expect you to be able to do, even if not all in one question. So a more reasonable version of this question that would show up on an exam might say something like, find a power series for x over 1 plus 4x squared. That's a more reasonable question because it doesn't require the integration, but it still requires that you remember that you have to take the x off the side and use the geometric series. So this is the one-step version of this problem. Okay? All right, now the other one, I mangled in the last section because I forgot to check the endpoints correctly. So for one, I'm just going to give you the quick version and I'll write solutions up and post them. I promise. I have no idea why they're not showing on the webpage right now. So if you look at a sum that looks like this, 2bn x minus 2bn over n squared, and you use the ratio test on it, the inequality that this should have reduced to is the absolute value of 2 times 3x minus 2 is less than 1. Now, I think there was probably some difficulty in trying to figure out what the radius of convergence is here. This is the correct equation, but it does not tell you the radius of convergence yet. Because to get radius of convergence, you have to have something of the form x minus a is less than r. X has to have no coefficient to get radius of convergence. So if I was doing this, I would take the 2 out and write it like this. You can divide by 2. 2 comes out of an absolute value. This is 2, and you can divide both sides by 2. And now you still can't say radius of convergence because there's this 3 here. But you could factor out a 3, and you'll get this. That's the radius of convergence because that's the center. Now x has no coefficient. That's A, the center of the series. That's R, the radius of convergence. So at the very least, you know this series converges on an interval that runs from 1/2 to 5/6. That's how some people try to eyeball the radius of convergence from this. It's easier to read it off from here than to try to reconstruct it from here. Yep.
From the first step, for the two, we have to do, you can't just 2 and 6 times 4.
If you want to multiply it in and do it that way, you're welcome to, but then you're just immediately going to divide by 6 anyway. If you want to get this form, right? I mean, it's up to you. I give you algebra at your own discretion. Yep.
Can you explain the integral part on number 2 again?
Yeah, absolutely.
Can you also do it, but -1 is less than 2 times 6 and times 2 less than 1.
Can I do what? 2 times what?
Set what you have down in the absolute value less than 1, also greater than -1.
Oh yeah, yeah, it's all the same. The reason that you might want to keep the absolute value is because it gives you an easy way to read off what the R is. It's up to you, man. You can do whatever you want. If you do this where you take the absolute values off with a -1 over here, you're going to get the same answer as I did. Get it right.
I did not do it.
Oh well then. You don't have to do it right. Okay, so when you check the endpoints of that, what you're going to find is that both series look like it's 1 over n squared and -1 to the n over n squared, both of which converge. I asked you for interval and convergence, so you have to check endpoints. When you plug the endpoints in, you should have gotten this series, this one. They both converge, so the actual interval of convergence includes the endpoints. Yep.
On the second one, we're supposed to assume that we should find an interval of convergence.
No. So like I didn't actually write the radius of convergence down. I'm gonna come back to number 2 and I'll actually talk about I meant to come back to do the radius of convergence on the second one. So I'm gonna do the integral again and I'm gonna talk about radius of convergence. So yeah, you should find, if I say find a power series, you should find the radius of convergence. You don't need the whole interval, but you should at least tell me the radius. Okay, so the integral step in problem 2. So let's just isolate just that part. So the integral step said we had d by dx of the arctangent of x equal to, all right, you guys make sure I got the right sum here. -1 to the n, 2 to the 2n plus 1, x to the 2n. I believe is what the series was there. The 2 has already been wrapped inside. Does this look correct?
Yeah.
Okay. So what I'm going to do basically is I'm going to think about getting rid of this derivative by putting an integral here. And the deal with power series is as long as you've got convergence, you can take the integral and you can stick it inside the power series. I'm not sure if this is more or less confusing, but this is what you're doing. And this is a constant. It doesn't change with the integral because it's just a number, right? So what we're doing is we're integrating x to the 2n. And the integral of x to the 2n is x to the 2n plus 1 over 2n plus 1, just by the power rule. Right? There's a plus c, but there's an infinite number of those plus c's, so we just pile them up and stick them outside as a single plus c. So the result of doing this is the sum of the constants don't change. But now I've got this x to the 2n plus 1 divided by 2n plus 1. And so I just took the 2n plus 1 and I wrote it over here as the constant. Yep. Arctangent to it. The only reason I did this is because one of the conventions about power series, you usually like to write them so that the coefficients are all collected together and the x is over here by itself. Yep.
Another question, or convention question. What is going on? When do you do n equals 0 and n equals 1?
Oh, I mean, okay. So when you take a derivative, so really this series right here, when we did this was a series from n equals 0. It started as that. The only time you destroy terms in a series is when you take derivatives, because when you take a derivative, you shaved off one of the pieces of the series, right? Derivative of a constant is 0. So you just drop it from the series. That's why you go from 0 to 1. But I'll point out, confusingly, that putting the n equals 0 in doesn't change anything because there's that n floating around in the problem as well, right? If you look at cn x to the n, and you take the derivative, you get ncn x to the n minus 1. So you can put 0 here, but you don't have to. Right? It doesn't change the series to put 0 here because you're just putting a 0 in front of the list. Now, radius of convergence for this question. When we were doing question 2, where does the radius of convergence actually change? Does integration change the radius of convergence of a problem? No, that's one of the big theorems, that integrating a power series does not change its radius of convergence. Does multiplying it by x change its radius of convergence? I've heard no and yes this time. Here's one way of thinking about it. The radius of convergence of combinations of functions are the most restrictive condition that you can put on them. So if you have two series that have two different radii and you combine them somehow, the radius you need is the one that's the most restrictive of the two. So they're both well behaved. But x, where does x converge? You can put any number you want into x, right? It's just x. So x converges everywhere. The power series converges where it does. So does multiplying by x change the radius? And the answer is no. Multiplying by x is fine. The only thing in everything that we did that's going to require us to change the computation of the radius of convergence is when we took this form and we replaced x with something else. We took that form and we used it on this. So whatever's in the box has to satisfy this equation. What did we put in the box? Well, we put minus 4x squared in there. So minus 4x squared it better be less than 1, or this formula doesn't even make any sense because you could be feeding in something that was bigger than 1 in absolute value. So whenever you do this substitution step, that's where you have to check for a change radius of convergence. In this question, I think this turns into x is less than a half. So the substitution into the geometric series is this. I mean, you could actually just do this with the ratio test as well and get the same answer. Okay. All right. Okay, so I'm going to reiterate here that this is famously, notoriously, this chapter, and especially this part of this chapter, is the hardest part of the calculus sequence. It's one of the places where people think this is the hardest part of the calculus sequence. So just keep practicing it. Like, this isn't as bad as it seems. It's new, so it seems weird, but the ideas here just require getting familiar with them. One of the most famous mathematicians of the 20th century, this guy John von Neumann, told a PhD student one time, it's like, how do you understand all this hard math? And he said, nobody understands it. You just get used to it. You got to see lots of it. You got to practice. Okay. Yeah, I mean, he didn't mean that you don't understand it. It means that there's no way to force understanding without exposure, right? You just have to keep seeing this stuff. The ideas aren't as weird as they seem. Remember, at the bottom, what we're trying to do here is we're trying to justify replacing functions with polynomials. That's all that's going on. It's just algebra because I want to replace functions with polynomials. Okay, so let's talk about Taylor polynomials. Taylor series. We have time to talk about Taylor series because we're going to kind of drift our way slightly into 1111, but we're kind of going to take our time through 1110 because we're going to nail down the ideas in here. We need these ideas. I mean, you guys do for sure. Everyone does. I use power series all the time. Okay. Scientists of all stripes use Taylor series constantly. Those of you that think you can get away with it because you're a computer scientist, no, Taylor series. The first thing a computer scientist does when faced with a function is replace it with a Taylor series. Because why would you do it with a function when you could have a power series instead? Okay. The idea with Taylor series is to answer the question, what if I just give you a generic function f, right? I just come along and say, here's an f. I don't want to, give me a power series for this. How do you find one? The answer is so far we don't have a method for that. If I just gave you a random function, like somebody comes up to you and says, oh, well, fine, that's all great and dandy. You can tell me what an arctangent is, but I don't ever work with arctangents. What I have is this damn exponential function that keeps showing up all over the place. And boy, is it inefficient to calculate. If only you could give me a power series for that. The answer is we don't have a method that will do that yet. We can't use this. This idea does not work on this function. So we want a way of, want to answer the question, how do I find a power series for more general functions? The answer should be pleasing to anybody in here who's an engineer or scientist of any kind, because we're just going to assume that it works and then figure out what it must have been. Right? That's the way a scientist thinks. Well, if it worked, what would it be? We'll find the thing that it should have been, and then we'll go back and show that it was the thing that we wanted. The applied mathematician's approach to the world. I found an answer and it works, therefore it was legitimate. Okay. So if we did have a power series for some function f of x, let's not deal with e to the x quite yet. We're going to use that as our first example. If I had a power series for f of x centered at a, suppose that f has a power series at x is equal to a. What would it look like? Well, it would have to be of this form. That's what a power series is, right? If it had one, there it is. So what we're going to do is we're going to try to figure out a way to write these coefficients as a formula from the function. Not just random c's, but actually figure out what these have to be. We got a hint last time in the demo. Okay. So what we're going to take advantage of is the fact that if I plug a into x minus a, 0 comes out. Right? A minus a is 0. So what I'm going to do, okay, well, if f of x is equal to c naught plus c1 x minus a, c2 x minus a squared. What's f of a? Remember, we're saying that function, whatever it is equal to its power series. That means whatever value of x I plug in, both sides have to be equal. So what's f of a equal to? What's the right hand side here? C naught. Okay, now I'd really like to know C1 in terms of f, but the problem is the best number to work with is a, and there's this damn x minus a here. So what I'll do is I'll take a derivative, which will destroy the C naught, and turn the x minus a into a 1. Yep. Oh yeah. You just keep going. You take a derivative, you plug in a, you get the next coefficient. You take another derivative, you plug in a, you get the next coefficient. It's like turning a crank on the derivative machine.
And then you do the integral of that.
No, there's no integration. The beautiful thing is no integration here. You just get the coefficient. We don't need to take. We don't even need integrals. All we're doing is using derivatives to destroy these terms so that I can isolate the coefficient. I mean, you'll see the pattern when I start taking derivatives. What's happening? If you look at f prime of x, well, what happens to this power series? Let's suppose that we're working inside the radius of convergence, so calculus is legal, right? So I've got some radius of convergence, calculus is legal. Again, this is the applied mathematician's approach, which is saying, let's just presume we have a radius of convergence, and then at the end, once we find the formula, we'll go back and figure out what it must have been. Okay, you take a derivative. What do you get? Well, the C naught is a constant, it goes away. The derivative of x minus a, there's a reason why there's no coefficients on the x here. The derivative of x minus a is 1. So this is just C1 plus, okay, the 2 comes down, and the power drops by 1, and then the 3 comes down, and the power drops by 1, and then the 4 comes down, and the power drops by 1, and so on. This polynomial. But what happens if we put a into this? That's a 0, That's a 0, that's a 0, and the next is a 0. There's zeros forever except for C1. Take another derivative. Once we actually have the pattern down, we don't need to do this again, right? We're going to identify what the pattern is, and it's going to tell us a fast formula for figuring out what these are. So the second derivative, okay, C1 gets destroyed because it's constant. The x minus a turns into a 1, so we have 2C2 plus 3 times 2C3 x minus a for the first, plus 4 times 3C4 x minus a for the second, and so on. So notice here, as I take derivatives, every power comes down and gets stacked up in this multiplication of powers, right? That seems familiar? When I take 4 derivatives of this, I'm going to get 4 times 3 times 2 times 1, which is 4 factorial. So what do you get when you put f prime prime of a? Plug a into this series. That's a 0, and that's a 0, and the next thing is a 0. And what you get is 2C2. So if you were a gambler or somebody tired of taking derivatives, you would look at this and say, okay, I bet what's happening here. So I noticed 0 derivative of f gives me C0. 1 derivative of f gave me C1. 2 derivatives of f gave me 2 times 1 times C2, which is like 2 factorial. I bet, on the basis of just these 3 cases, that if I take n derivatives of f, and then I put in a, what's going to happen is I'm going to get the n factorial from all the powers that came down and stacked up like this, and then Cn, the nth coefficient. And every one of those fits the pattern. This thing is no derivatives of f, right, is equal to 0 factorial C0, 1 factorial C1, 2 factorial C2. If you took another derivative, you're going to get 3 factorial C3. So this equation is true for all values of n. Now, what is the goal of all of this? The goal was I wanted to find these. I want a formula for C0, C1, C2, and C3. These don't tell me anything about what they are. But if I can put them in terms of the function, now I've got something I can calculate. So I could solve this equation for Cn. This, almost all of you have seen before. These are so special, they have a name. These are called Taylor coefficients. And they were invented by Newton about 100 years before Taylor knew that they existed. Those of you that know what a Maclaurin series is, it's even better because Maclaurin wrote a textbook 40 years after Taylor wrote his book, where he popularized Taylor coefficients where you put this a equals 0 in, and then he gets his own series called Maclaurin series, which he didn't discover either. So none of these guys discovered what that was named for. Yeah, they wrote textbooks. Taylor didn't know any of the other math in the world, and Maclaurin wrote a textbook. Anyway, we'll get there when we get to the Maclaurin series. So the point is that gives me a formula I can use to actually tell you specifically what these are. So now I can say, well, I don't have random C0, C1, C2, C3 anymore. Now I can say, if f has a Taylor series, if f has a power series at x is equal to a, it looks like this. F of x is f of a plus f prime of a x minus a plus the second derivative of f at a times x minus a squared over 2 factorial plus the third derivative of f at a over 3 factorial x minus a to the third and so on. And those are numbers you can just compute. You can take derivatives and plug in numbers, right? You can find these. These aren't random anymore. Usually this is written like this. This is what's called a Taylor series. After a guy that wrote Texas. So what is the point? What's the point of this? The basic idea is now it's not just that I have power series, it's that I have given you an algorithm that you can use to find the power series. Okay? So we can actually use this formula to find power series for functions. So there's some details we're going to have to talk about next time, like how do I know this is actually equal to the function? What sorts of functions can I do this with? What's the first obvious thing you need to be able to do to have a power series? I mean, if I'm going to compute all these numbers, f of a and f prime of a and f double prime of a and f triple prime of a, what do I have to be able to do? I better be able to find the derivative of the function, right? So if I run out of derivatives, I can't take a power series. So it has to be infinitely differentiable, which is actually a pretty strong condition, right? So without delving too deeply into any more theory here, let's actually just find one. The question that we asked earlier was, what is the power series? I wrote this down earlier. I said, I, at some point, gave you the power series for, oh, thanks. That's going to be great on the video. I guess I can just be louder or speak in the gaps. Anyway, I'm going to try to block that out. Badly. So what do I need to do to find the power series for this thing? I need to shift the rhythm on me there. I'm actually going to need to compute these pieces to get this, right? So what I'm going to do, and some of you have done this before, it's actually easiest to calculate this if you sort of take a table-wise approach. So when you're computing these things for the first time, it's convenient. That's irritating. It's convenient to actually just calculate all the bits that you need and build up the coefficients that you're after. Now I've chosen e to the x on purpose because e to the x has the nicest derivatives in all of the universe. So no derivatives of e to the x. It's e to the x. Oh, and we're doing about x equals 0. So we're choosing a center of 0 this time to make this computation even easier. So we're going to compute a Taylor series using this formula. That means I need to build these coefficients and look for a pattern. All right, well, I'm going to very quickly do some derivatives of b over here. You guys are welcome to do this with whatever method is your favorite. Now, I don't want functions because this tells me I'm supposed to take the derivative and then evaluate it at the function center, right? So I'm going to take all of these guys and I'm going to apply, or I'm going to put a into the function. So this is the nth derivative of f, the non-derivative of f at x. Put in x equals 0 and you get e to the 0, which is 1. Oh, what a nice power series this is. Now I will tell you, normally these derivatives are not just all the same, and these numbers are not just all the same. Yep.
Wait, sorry, why is it E0 over and over again? And not
because what I'm doing now is I'm evaluating the series at the center. These coefficients are all evaluated at the same number a. So as soon as you tell me what you want to be in the series, x minus a, what the a value is, that's the number that makes all these things work. Because really what you're doing here is you're making the derivatives match at that one point. So you apply whatever the a value is over and over and over again. So the derivatives came, I mean, this is artificial because e to the x always has the same derivatives. This is the non-derivative, the first derivative, the second derivative, the third derivative, the fourth derivative.
So the value of a function at f equals a.
Yes.
A.
Derivative first, then plug in the a value. So whatever this function is, I'm putting the a into it. Then what do I get for the coefficients? This is where the n's are going to come in. 1, whatever this value is, divided by 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial. right? Because that formula says there's supposed to be these n factorials running around in the background. And what you've done when you finish here, this is C0, and this is C1, and this is C2, and this is C3, and this is C4. It's important to have some way of keeping track of which numbers are attached to which values of x, which powers of x. So what that tells you is that e to the x, which is C0 plus C1x plus C2x squared plus C3x to the third plus C4x to the fourth can be written 1 plus 1x plus 1 over 3 factorial x squared plus 1 over 3 factorial x to the third plus 1 over 4 factorial so on. And if you're willing to go 1, 2, 3 infinity, you can guess that the general pattern here is going to look like this. So this is where that formula for the power series for dx centered at x equals 0 comes from. Calculate a pile of coefficients, you associate them to the correct powers of x, and the thing that comes out is a polynomial that matches e to the x in its value, in its tangent line, in its second derivative, in its third derivative, and fourth, and so on. So it's sort of uber tangent to e to the x. Yep.
This works for any infinitely differentiable.
Any infinitely differentiable function can be written this way. Well, so if you try to center a power series, okay. All right. I'm going to give you the last thing I'll say is what's the worst function I know? Let that be f of x, except give it the value of 0 at x equals 0 to avoid the fact that there's an asymptote there. I wrote this on the board the other day. This is a function that goes like this. So, oh, and then you just put a dot right there to make sure it's defined at 0, right? So you can build a family of functions like this. This is not even continuous, but if you start chaining powers of x onto the front of it, you can make it continuous but not differentiable. And you can make it have as many continuous derivatives. So like this one has 2 continuous derivatives, but then no more. Which means the Taylor's this can't have a Taylor series because I can't infinitely differentiate it. Good question, by the way. All right, so keep it up. I know this stuff is tough. Just keep it up. Get used to it with time.
Yeah.
Oh, okay. I didn't even know. I'm so scared of that.